welcome to Cognito Key. Today, we are going to unlock a really fascinating puzzle. How do you heat something that is actually designed to stop electricity in its tracks? You know, we're all used to the idea of fire, right? It heats things from the outside. And we know electricity can warm up metals. But what about insulators, things like plastic or wood? Their entire job is to block electric current. So how on earth could you possibly heat them, especially from the inside out? Well, as it turns out, technology has found a pretty clever way around this. It's a method that actually uses an insulator's own properties to create heat, all without a single flame. And it's called dielectric heating. Now, to really get how this works, we first need to meet the star of our show, the dielectric material itself. So dielectric is really just a bit of a fancy name for an electrical insulator. We're talking about materials that have very few free electrons, which means they are terrible at conducting current. Think about all the everyday things around you, the plastic on your phone charger, a wooden table, even a glass window. Okay, so if you could zoom way down to the molecular level of, let's say, a piece of plastic, you'd find that its polar molecules are all just jumbled up. They're pointing in totally random directions. There's no order at all, just a kind of chaotic molecular soup. Now, this is where the magic really starts to happen. When we put that material inside an electric field, all those randomly arranged molecules, they instantly snap to attention. They align themselves perfectly with the field. This sudden, super organized alignment is a really crucial process, and it's called polarization. So the molecules are all lined up. That's great. But that alone doesn't create any heat. The real secret isn't that they line up, it's all about how we make them do it. You see, we don't just use a steady, boring electric field. Oh no, we use one that alternates, flipping its direction back and forth at an incredible speed, somewhere between 10 and 50 million times every single second. I mean, that's so fast, it's actually in the radio frequency range. So here's how it all comes together. First, we apply that high-frequency field. The molecules inside, they desperately try to keep up, flipping back and forth millions of times a second. Can you just imagine all that frantic movement at a molecular level? It creates a huge amount of internal friction. And just like when you rub your hands together to get warm, that molecular friction generates powerful heat, warming the whole material up uniformly from the inside out. Now, in the world of electronics, this effect is called dielectric loss. It's basically a tiny bit of energy that gets wasted as the molecules struggle to keep up. At the low frequency of, say, a wall socket, this loss is nothing, it's insignificant. But when you crank that frequency up millions of times, all that wasted energy adds up and becomes this powerful engine that generates intense, controllable heat. But of course, like any technology, it's not a perfect solution for everything. It comes with its own very specific set of pros and cons. Okay, so let's look at the good stuff first. Its biggest advantages are that it's fast, it's controllable, and it heats things perfectly evenly. Plus, its ability to heat non-conductors is its unique superpower. But on the downside, it's not very efficient. It only converts about half of the electrical energy into actual heat. Those high frequencies can also interfere with radio signals, and it really only works on materials that have high dielectric losses to begin with. So where does all this clever science actually show up in the real world? Well, you might be surprised just how common it is. It's used all over the place. In food processing, for quick defrosting and cooking. In manufacturing, it uniformly preheats plastics before they're molded. In medicine, it's used for sterilizing equipment, and even for a therapy called diathermy, which warms deep body tissues to help relieve pain. It's even the tech behind what's called electronic sewing, which seals plastics together for things like raincoats. If there's just one thing to remember from all of this, let it be this. Unlike an oven or a fire that heats from the outside in, dielectric heating works from the inside out. That ensures a perfectly uniform temperature all the way through. This technology, it lets us precisely heat things we once thought were, well, unheatable. And that creates all sorts of new possibilities in medicine, manufacturing, and beyond. So it really makes you wonder, what kind of problem could you solve with this power? If you enjoyed this explainer, please subscribe to Cognito Key for more deep dives into the world of science. And of course, don't forget to like and share. Thanks for watching!